Good morning. Let me share my screen and we will continue our lectures. Okay, here is my screen. So, what we did yesterday, we considered a weak product for Gaussian functionals. So initially we have separable real Hilbert space. We have white noise, Gaussian white noise Xi here. We supposed that sigma field of random events is equal to sigma field generated by Xi. Then we discussed that if alpha belongs to L2 omega Fp, then it can be uniquely expanded into Ito-Wiener series, which consist of orthogonal summands, which are generalization of Hermite polynomials on infinitely dimensional case. We know that this expansion can be recovered if we use multiplication of alpha on the stochastic exponent. Stochastic exponent was introduced by the following formula. This is psi h minus 1/2 of norm of h square. We defined Fourier-Wiener transform of alpha as the element h as an expectation of product alpha on our exponent. Then we discussed that it can be checked that Fourier-Wiener transform of alpha is equal to the sum from n equal 0 to infinity Qn HHH. So it is analytic function and elements of the expansion Hilbert-Schmidt forms Qn can be obtained as a derivative of Fourier-Wiener transform at the point 0. Then finally we defined for two random vectors the weak product alpha multiplied on beta as follows. It must be such a random variable that its Fourier-Wiener transform is equal to the product of Fourier-Wiener transform of alpha and beta. Of course, it can be checked that weak product is not defined for all random variables, but we check it several examples. For example, if alpha and beta belong to say polynomial from Xi, namely they have finite Ito-Wiener expansions. Bn Xi. Then alpha beta is well defined, and one can check that it is equal to the sum from n1 or nm equal 1 to nm. Here is, excuse me, lambda an bm. Here is xi. Here we have n plus m. As we mentioned from the first look, weak product looks very complicated procedure. And we expect some new properties relatively to usual product. But it occurs that if we have two orthogonal subspaces, for example, if we have M1, M2 are orthogonal subspaces, of H P1, P2 are corresponding projections then for such an that an is equal to an from P1, so on P1. So I just write the condition that an depend only on the projection of the element in H onto the space M1, and the same Bm, which is equal Bm from P2, we have that weak product an xi on Bm xi is equal to the usual product an xi multiply on Bm xi. It is interesting to look at the partial case of this formula, namely consider E1, which is orthogonal E2, and such that norm E1 is equal to norm E2 equal to 1. Then we already discussed that if I take Hermite polynomial Hn psi E1 and take a weak product of Hermite polynomial Hm psi E1, then we must get the Hermite polynomial of degree n plus m from psi E1. We discussed this when we considered weak product for functionals from one standard Gaussian variable. But since this orthogonality, we have the following relation. If I consider Hn from psi E1, weak product with Hm from psi E2, then it will coincide with the usual product Hn psi E1 multiply on Hm psi E2. That's all. We have some good examples when the weak product coincides with usual product for independent multipliers. But of course, this independence is generated by the orthogonality in initial Hilbert space. As I said yesterday, we at the end of the previous lecture, now we have enough tools and enough objects constructed, which are constructed in the abstract situation. So, as we mentioned in the beginning of this lecture, we have abstract Hilbert space, white noise there, and some abstract construction like Hilbert-Schmidt forms, Hermite polynomials, Ito-Wiener expansions, and so on. And now is the time when we can try to apply developed machinery to more familiar objects. So now we will discuss Wiener functionals. Namely, we will go to the following situation. Let me. Now I'm specifying space H. It will be L201. It is a space of all square integrate real valued functions on the interval 0, 1 with the usual scalar product. Now we have to define the white noise there. How it can be done? Suppose that W T belongs 0, 1 is a standard Wiener process. A Wiener process. Then you remember that for any H which belong to our L2 0, 1, the Wiener integral from 0 to 1 HS dws is well defined. Yes. And let me recall you that it has a normal distribution with 0 mean and integral from 0 to 1 HS square ds as variance. So one can see that stochastic integral, Wiener integral with respect to Wiener process has the same property as white noise. Actually, you remember this was the main property of white noise. Its scalar product with the elements of the space must be a normal variable which is centered and has variance equal to the square of the norm of H. So one can say that now formally we can define psi as a derivative. I will put here a dot of W. Why? Because formally, this is just formal, not rigorous mathematical formula. This integral can be written as hs dws is equal to integral from 0 to 1 hs w derivative s ds. Of course, this is just formal thing, formal, because we know that, excuse me, we know that Wiener process has no that Wiener process has no derivative. It has non-smooth trajectories, and by the way, this integral from 0 to 1 hs dws is a limit when n tends to infinity. Here is the sum from k equal 0 to n minus 1 ck delta w tk, when such a function sum from k equals 0 to n minus 1 ck indicator of tk plus 1, such function approximates the function h in L2. So you see that one can construct a Gaussian white noise as a family of integrals, deterministic integrals. Sometimes such integral is called Wiener integral, because the Wiener was one of the first persons who began to study it. And in this case, we have Gaussian white noise related to the Wiener process. So there are no any surprise that in this case sigma field generated by Xi coincide with the sigma field generated by the Wiener process W. So well, we will say that we have a functional square integrable functional from Xi. It means that we have a square integrable functional from the Wiener process. Why it is interesting to consider to study such partial case? Because of several reasons. First reason is that we have a well-developed theory of stochastic differential equations with the Wiener process. So we have a lot of statements about the functionals from Wiener process and a lot of questions about it. So maybe our calculus will help us to solve such questions. And also we can interpret abstract elements of our calculus in the familiar objects as the familiar objects in the Wiener case. This is first reason. Next reason is that jumping to Wiener case, one can expect that we will have an ability to consider another Gaussian processes, maybe related to Wiener processes, but we can build some elements of stochastic analysis for more wide class of Gaussian processes than only Wiener processes. It occurs that two this hypothesis became to be true, and now transfer our abstract construction onto this case. First of all, let us consider E to Wiener expansion. It will not match. So what we need, we want to understand the following. Let Q n be the element of L2, excuse me, of, yes, L201 tensor n power and symmetric. Then what is Q n from xi? Now, of course, one can say we already know what it is. We just have take some first normal basis in L201 and organize infinite dimensional Hermite polynomials related to Qn. But we already have seen that our white noise is generated by the integral with respect to Wiener process. So maybe here we also must have something like integrals with respect to Wiener process. And this is true. To do this, let us proceed as follows. First of all, let us understand what is this. What is this? Okay. To understand this, let me recall you that now the tensor product of L2 on itself n times is can be interpreted as a space again L2 on 0, 1 and in n power. And it is natural. Maybe you remember from different courses, functional analysis course, from differential equation course, that when we say Hilbert-Schmidt operator in the space L2, 0, 1, we can also say this is integral operator with square integrable kernel. Exactly the same happened here. So this tensor power is L2 onto 0, 1 in n. Correspondingly, one can relate with the Hilbert-Schmidt form Qn the kernel Qn small which belong to L2 0, 1, 0, 1 n. Moreover, since Qn is symmetric, then Qn also is symmetric. Namely, Qn from T1 Tn is equal to Qn from T sigma 1 T sigma n, where sigma is arbitrary permutation from the set of all permutation. Is arbitrary. Permutation. And finally, for all H1, Hn belonging to L2, 0, 1, the action of Qn on H1, Hn is equal to the multiple integral from 0 to 1 n times qn t1 tn ht1 h1 t1 multiply hn tn finally and dt1 dtn. Okay. We have such a nice representation for Qn, and it remains to get the nice representation for Qn psi psi psi. In order to do this, let us try to do with the simple kernel Qn. To simplify our considerations, I will consider n equal to 2 and make a main conclusion in this case. The general case can be considered in the same manner. So consider a case when n equal to 2, and I will take simple step kernel Qn. Namely, I will consider the following Q2, Q2. I will consider the following partition: 0 equal to T0, less than T1, less than Tn equal to 1. This is the partition of 0, 1. And I will consider Q2 from S1, S2 will be equal to the sum from 0 less, excuse me, K1 is not equal to K2. Here is C K1, K2. Here is indicator of T K1, T K1 plus 1. Multiply on the indicator of T K2, T K2 plus 1. And this is from S1, this is from S2. So what happened? Let me try to draw a picture. Here is a picture. We have a partition of our interval, and we just define our function on this square, on this rectangles. We don't consider rectangles which are on the diagonal. Here is so we just define our functions there. So if we have t k1 tk plus 1, here is tk2 plus 1, and here is value c k1 k2. Okay. So we have such a step function. Of course, to be symmetric, let's recall that it must be symmetric, must be equal to Q2 S2 S1. We have the following property CK1 K2 CK2 K1. And now we have the following kernel. Let us define it now Q2 from Xi Xi. To do this, let me proceed as follows. You remember that in the definition of multilinear Hilbert-Schmidt form from Xi, we have the following orthonormal basis. E1, excuse me, Ek, k is greater or equal than 1, is orthonormal. Basis in L2 0, 1. So what I will consider now I will consider special choice of this orthonormal basis. Namely, I will define E1 is equal to indicator of T0 T1 divided on the square root of delta T0. Then E2 will be indicator of T1 T2 divided over square root of square root of delta T1 and so on. En is the indicator of Tn minus 1 Tn divided on the square root of delta Tn. Tn minus 1. Okay. And then I don't care about other orthonormal other vectors of this orthonormal basis. Why? Because you remember simple statement from the function analysis and linear algebra that if you have some orthogonal system, here is E1, E2, En, it is evidently orthogonal, then you can enlarge this system up to the basis. So now I take some continuation of this construction. I don't care about this. K is greater or equal than n plus 1. Then let us now consider Q2 Xi Xi Xi. It is equal to the sum, as we discussed, sum from K1 not equal to K2. Now, here what I have. I have here the following. C K1, K2 multiply on the square root of delta T K1 minus 1. Here is square root of delta T K2 minus 1. Multiply on the product. Here we have square root 1 or square root delta tk 1 minus 1 indicator of tk1 minus 1 tk1, yes, and psi here, and the same indicator of delta t, square root of delta t, k2 minus 1, indicator of t, here is weak product, t k2 minus 1, tk2, and here is psi, that's all. Let us consider this weak product. First of all, we take only such summation where k1 is not equal to k2. So these two vectors are orthogonal. Since then, weak product coincide with a usual product. Okay, so I will continue, and let me continue with the eraser. So we have just a usual product. We have just usual product here. Moreover, now let us recall what is the definition of white noise. What is the definition of white noise? It must be the integral from this function with respect to Wiener process. So I can continue. I can continue with the following formula. It will be like k1 is not equal to k2. Here is ck1, k2. And here is, you see, I can subtract this outside of integral and then make a annihilation. So what is remaining? Integral from tk minus 1 up to tk1 dw multiply on the integral from tk uh, 2 minus 1 up to tk2 dw. That's all. So it's equal to, now you see that it is exactly the multiple integral. I will use, now I am using symmetry of coefficient ck. This is 2 multiple integral from 0 to 1. Here is from 0 to t2 our kernel q2 t1 t2 dwt1 dwt. Yes, here this formula is trivial because we have step function, but if you look at the beginning and the end of the formula, then we can imagine that there are no any step function. And one can assume that this formula remains to be true when we have arbitrary symmetric square integrable kernel Q true. And this is true. In this case, we will have well-defined Wiener integral. Why? Because if we consider this integral inside, then it is adapted to the sigma field flow generated by Wiener process up to the moment t2, and we have here integration. So everything is okay, and we have such a nice representation for our multiple Hilbert-Schmidt form from the random Gaussian white noise Xi generated by the Wiener process. This formula remains to be true in general case. Let us just write it. So if we now have Qn, which belongs to L2 01 in n power symmetric, then it is in one-to-one correspondence with Qn, which belong to L2, 0, 1 in n power, and also is symmetric under permutation of all arguments. So Qn acting on H1, Hn is equal to multiple integral from 0 to 1 n times Qn T1 Tn H1 Tn T1 multiply, excuse me, multiply on Hn Tn dt1 dtn, and finally Qn xi is equal to n factorial. You remember, here we have 2, but 2 is 2 factorial. Why we have 2? Because we have permutation k1, k2 or k2, k1. There are only 2 permutations in case we have 2 variables. But if we have n variables, we have n factorial permutation. So we have this n factorial there. And here we have integration of a simplex. Let me firstly denote it and write the integral, and then I will explain the notation delta n. Qn T1 Tn dw T1 dw Tn, and then I will write delta, not a explanation for delta n. This is a set of vectors T1, Tn, such that 0 is less or equal than T1, less or equal than T2, less or equal than, and so on. They are ordered, yeah? Less or equal than 1. So delta n is just simplex, yeah? Okay, so now we have understanding what is Qn, and let me note that despite we have here in the right-hand side the integrals with respect to Wiener process, multiple integrals, still it is a not very complicated probabilistic construction. You see this sum here. It is easy to imagine what happens in a multidimensional case. So it is not already a very complicated stochastic integral. And Wiener was first who studied this integral. So this integral often are called by Wiener multiple integrals. And then finally, if we have alpha, which is square integrable, functional now from the Wiener process W, then alpha can be uniquely represented as a sum of such multiple integrals. So now the e to Wiener expansion for alpha, here is n equals 0 to infinity, can be written as follows. It will be some integral with respect to simplex. Here is Qn with tilde, T1 Tn, dw T1, dw, and so on, dw Tn. And let me note that I put here Qn with tilde because it is related to the previous one function like n factorial multiply Qn. Because of we have no n factorial before the integral, yeah. And of course, we have the well-known for us properties that expectation of alpha is just Q0, and expectation of alpha squared is equal to sum from n equal 0 to infinity integral delta n qn t1 tn square dw t1 dw tn. Please check. Oh, excuse me, not w, not w, of course. dt1 dtn. Please check that this formula exactly coincide with the formula sum of n equals 0 to infinity n factorial norm q n square. And because we have 1 factorial, we have inside, and when we put it in square, we have 2 factorials, and 1 disappeared because we have not integration only over simplex, but we must have the integration over cube. So 1 factorial remains. Okay, now let's go further and look for the stochastic exponent. Stochastic exponent now, as we defined it, has the following kind. This exponent here is psi h minus 1/2 of norm of h square. Excuse me. And is equal to now exponent. Here is integral from 0 to 1 h dw minus 1/2 integral from 0 to 1 norm of h, excuse me, oops, here is h or h square dt. Now we want to have its expansion, and to understand this, it is good to consider not this expression, but put in this expression here and here the variable t. For a moment. So to do this, I will consider such a function. Xt is equal to exponent of integral from 0 to t h dw minus 1/2 integral from 0 to t h squared ds. Why I am doing this? Because I want to use now Ito formula. Ito formula. Ito formula. As we said today, the integral with respect to Wiener process is not a Lebesgue-Stiltiez integral, because the Wiener process has no smooth trajectories. Yeah. And we discussed that it is defined like a limit of the integrals from the step functions. Yes. But still, one can try to have something like Newton-Leibniz formula for Ito integral, for Wiener integral, and so on. And people did this. And this is with very simple and beautiful construction. How it can be done? Let us consider fundamental property of Wiener process. Quadratic variation of Wiener process. Consider a partition equal to T0 less than T1 less than Tn equal to 1. Now I am considering the sum from k equals 0 to n minus 1 of delta W of increments of W related to this partition in square. Yeah? In square. And it occurs that in L2 it tends to 1 when maximum tk plus 1 minus tk over k equals 0 to n minus 1 tends to 0. So you see, the Wiener process has non-regular trajectories. We already said that it has continuous trajectories, it is well known, but also it is well known that it has no derivative at any point with probability 1. It has non-smooth trajectories. And this statement also proves this, because if you consider smooth function like a sine or exponential or something else, then quadratic variation will go to 0, not to some positive number. Okay, please check this as an exercise. It is easy. It is easy, but must be calculated. This is exercise. Okay. Then when we have it, then it becomes to be natural to say formally that dw, differential w square, is equal dt. This is formal, but very useful. Thing. Why? For example, consider differential of some smooth function from Wt and t. What will be? It will be, as usual, f prime with respect to the first coordinate, ft, t, dwt. Yes, I take the derivative with respect to the first coordinate, and correspondingly to this, I take the differential of the first coordinate, this wt, plus I take the derivative with respect to second coordinate, as usual. Yes, it is trivial, it is from analysis, but you see, here I have to consider not only the derivative of the first order, but plus 1/2 f2 prime 1 1. Here I take wtt as usual, but here what must be placed? Wt in square. Yes, this is from Taylor expansion. But now it is dt. It is dt. So I just write instead of this, I write dt. And this is a formal way. Of course, this is not a proof. This is just formal calculations, but very useful. This is a formal way to get the expression which is called Ito formula. This is Ito formula. It is named in honor to Kiyoshi Ito, well-known Japanese mathematician who invented this formula for integrals, even for integrals for Wiener process formula. So we will apply such formula to this process X, Then what we will get? Let me try to calculate dxt. It must be very useful that we have here exponent, yeah? Because exponent after differentiation remains to be exponent. So I will say that it is xt, yes? But then if we take exponent with respect to this variable, then what we will have? We have h dwt, yes? So ht dwt. Then what we have? Then we must have the derivative with respect to this coordinate. So with the sign minus, we have the differential minus 1/2 x t. This 1/2 comes from this 1/2, from this 1/2. 1/2 xt h square t dt. But we have this this term now. Sometimes this term is called itosummand in this formula. So I have to say plus second derivative. It is the same xt, then 1/2 and what? ht squared dt. And you see that these two terms are cancelled. So finally, we have the equation dxt is equal xt ht dwt. Moreover, I know the initial condition for this equation. I know that x0 is equal to 1, put t equal to 0. So I have such simple but stochastic differential equation. It is very similar to the equation for the exponent in the usual theory of ordinary differential equation. Since then, we understand that that arise a new reason to call stochastic exponent by its name. Moreover, one can solve this equation using successful approximation. Approximations. So x0 equal totally 1. x1 is equal 1 plus integral from 0 to t hs dws and so on. xn plus 1 is equal 1 plus integral from 0 to t xn s dws. And so on. And one can check that now xt is equal to the sum from n equals 0 to infinity. Here is integral over simplex delta nt h t1 h t2 and so on htn dw t1 dw tn. Okay, so we have such a representation for our solution, which we obtained with the help of Ito formula and stochastic differential equation. So today we get the representation of square integrable random functionals from Wiener process. We get the right expression for stochastic exponent, and then we will apply this to different equation with a weak product or extended stochastic integral with respect to Wiener or another Gaussian processes next time. Today, that's all. Thank you for your attention, and maybe somebody have questions or comments. If no, then again, thank you for attention, for your attention, and bye up to the next week. Bye.